Welcome once again to our science tutorial. We are still on physics mail on science tutorial, and remember that this is a special edition of the physics mail because we are concentrating on the WASI and UTME revision. That's the West African Senior School Certificate Examination and the Unified Tertiary Matriculation Examination. Also for National Examination Council exams. So this is a special edition, and we have been looking at various topics. We want to just revise various topics. So we are still on the concept of measurement on physics mail. Remember, we have looked at the basic terms in measurement, talking about our quantity, dimension, and units. And we're able to look at the fundamental quantities and the derived quantities. We also looked at the dimensions and the units of fundamental quantities. We also considered how we can actually obtain the dimensions and the units of the derived quantities. And we saw some examples, and these questions were given to us for us to just solve as an evaluation to know how far we have gone. And I know that you have solved it based on our previous video. So we're going to do a correction so that you actually know whether you got the answer. Remember to stay away from every form of distraction, whatsoever thing that will distract you, that will make you not to participate fully in this particular class, in this beautiful class. Just stay away from it. Get your writing materials and every other thing that will make your study efficient. Just make sure that they are ready with you. All right, so let's look at the corrections to this. Remember, we are doing this so that our students will have excellent performance in their external exams, especially the UTME and the SSCE, being organized by WAEC and also by NECO. All right, let's quickly look at the correction to these questions. I hope you still remember the steps we took while obtaining the dimension and units of the derived quantity. So let's go through this. The first one we are looking at acceleration. Acceleration, and we say that acceleration is velocity change. Velocity change all upon time. Okay. Now we say for us to obtain the dimension and the units of a derived quantity, this is a derived quantity, we have steps. The first step is that we need to write the formula for calculating that particular quantity. And to calculate acceleration, we use this formula, velocity change all over time. Now, we say we'll make sure that that quantity is the subject of formula. So here, acceleration is the subject of formula, and it is the dimension and the unit of acceleration that we are trying to find. Okay, that's the next step. Then we are also asked to express all the quantities in terms of the dimensions of the fundamental quantities. So we have actually obtained the dimension of velocity before. Velocity is length per time. Length per time, that's the dimension. Length per time. Now, time itself, so velocity is length per time. Velocity change has the same dimension as velocity, so all upon time. So length per time divided by time, that's what it is, because velocity has dimension of length per time. So this is representing velocity. So we can now write this as length per time divided by time. So this divided by time. Now applying the principle of mathematics, this length per time times 1 over time. Oh yes, because when you change division to multiplication, the next term there will be inverted. Your principle of fraction anyway. So we have length times 1 is length, time times time will give us time squared. So the dimension of acceleration will be length per time squared. Or I can write it as length per time squared. That's the dimension. That's the dimension. Then we say the unit now will be obtained by replacing these dimensions with the appropriate unit. So Length is measured in meter and time in seconds, or I can write it as meter per second squared. So this is the unit of what? Of acceleration. That's how we obtain dimension and units of derived quantity. And this one is for acceleration now. So go through it again. We have velocity change over time, then velocity is length per time, that's the dimension, all upon this time. Now physics have just ended, we're now applying mathematics anyway. So when we do that, this means length per time divided by what? Time. And that's what we did here to make it clearer. So we change division to multiplication, then we have this. At the end of the day, we arrive at this length per time. Remember, we say if we don't want to put this division, that's this part, this line, we have to replace that with a negative what? A negative sign. Alright. Now, when we replace the dimension with the appropriate unit, we can now obtain the what? The units of the quantity. Okay, that's for acceleration, and I believe you are taking note of that. So let's quickly go to force and see what we are going to have in force. Let's see what we're going to have in force. They say that force, second one now, force is mass times acceleration. We have written the formula, and force is the subject of formula here. So we move on. What's the dimension of mass is m. Now what's the dimension of acceleration? That's what we just obtained, length per time squared. So it means that the dimension of force now will be mass times length per time squared. I can alternatively write it as mass length per time squared. That's the dimension now of what? Of force. Now the unit of force will give me mass is measured in kilogram, length in meter per second square, or I write it as kilogram meter per second square. That's the unit of force. But the SI unit of force is what? Is Newton. Is Newton. The SI unit of force is Newton. That's the SI unit of force. Is Newton. Now, this SI unit of force, which is Newton, is equivalent to this. And we can now do that 1 Newton, we can now say that 1 Newton now, 1 Newton is equivalent to 1 kilogram meter per second square. So a Newton is equal to 1 kilogram meter per second square. That's a Newton. 1 Newton is equal to 1 kilogram meter per second square. That's 1 Newton. Alright. So the SI unit of force is Newton. So when we do calculation, when we calculate the value of force, we don't normally use kilogram meter per second square. We just use Newton because that's the SI unit. So Newton is a derived unit, which is equivalent to what? Kilogram meter per second per second square. Okay. Now finally, let's look at the third one, which is momentum. Momentum we say is mass times what? Times velocity. Momentum. Mass has dimension of capital M, and then velocity is length per time. So we have the M uppercase letter L time per time, or mass L per time. So we have this. This is the dimension of momentum, mass times velocity. The whole of this is velocity, we have seen that before. Then this is mass, that's the dimension of mass. And when you multiply this, you arrive at this. Then this will give me mass is kilogram meter per second, or kilogram meter per second. Okay. So the unit of momentum is this. Why this dimension is this. The unit of momentum is this. Kilogram meter per second. The dimension is mass. Length times length per what time? Mass length per time. Mass length per time. That's the dimension of momentum. Now, one can actually, units and the dimensions, or especially dimensions of units, especially the unit can be written in alternative form. We can write a unit of momentum in another form. We can write that also. We can write it in another form. We can actually say that Newton seconds. Newton seconds is equivalent to kilogram meter per second. Someone will say, is it possible? Yes. Let's prove that Newton seconds is equivalent to kilogram meter per second. All we need to do is to check Newton. What is Newton? Newton is what? Kilogram meter per second square. That's Newton. Or I can write it as kilogram meter per second square. That's Newton. We have seen that. Newton, 1 Newton is this. Or we can write this 1 kilogram meter per second square. So this is equivalent to Newton. So Newton is this, so times seconds. Somebody will just make mistake of multiplying this now. So remember that this is kilogram meter per second square, then times seconds. Now a second, we cancel one of these, we have this. So we are left with what? Kilogram meter per second, that's over second. Now you see, this is this. So Newton seconds is equivalent to kilogram meter per what? Per second. It's equivalent to it. It's equivalent to kilogram meter per second. All right, we are going to go on a break now. When we come back, we just look at the final part on this concept of measurement, where we're going to look at dimension analysis. Dimension analysis. We just see how we can actually use the principle of dimension to find arbitrary values, arbitrary constants in a given dimension. For example, one can be given something like this: m raised to power s, l raised to power y, t raised to power z. And you are asked, if this is the dimension of pressure, for example, what will be the value of x, y, and the word z that will make this dimension to become the dimension of what? Of a pressure. Of pressure. So that's what we are going to look at. Continue to read your books and study hard because of your forthcoming exams. Remember, proper preparation will prevent poor performance. If you don't want to perform poorly, then you need to prepare properly. God bless you.